the previous lecture. So previous lecture, we found that there's this geometric invariant called intersection numbers. Okay. And they compute the amplitudes in particular periods. Or that's the proposal. And then we consider two separate limits of that. One is when alpha prime goes to 0, and in those cases, intersection numbers coincided with low energy limit of various string groups. On the other hand, the opposite limit, alpha prime going to infinity, they collapsed to this kind of invariance, which I guess I called plus hat, which is the formula of CH1. And then in certain circumstances, more precisely, when this intersection number was either independent or homogeneous in the coupling constant in alpha prime, then the two limits were actually computing the same object, and they were equal. And the question that we wanted to ask in this talk is, well, can this be a more general phenomenon? Well, the answer seems to be yes. And in order to flesh it out, let me consider what will happen. A similar kind of localization will happen for Feynman integrals, or in the study of Feynman integrals. Okay, so what are Feynman integrals? I really mean Feynman loop integrals, as opposed to so one example of such a thing is, let's say you have a box diagram, and there's some momenta P1, P3, all massless incoming. Okay? And there's some loop momentum, let me put it here. And you can define an integral associated to this object. And traditionally, this would be defined as integration of the loop momentum in 4 space-time dimensions. And then here we would have L squared, we have L plus P1 squared, all parameters, P1, P2, and the last one. Such integrals, Feynman integrals in general, is that they often don't converge in V is equal to 4 space-time dimensions. And because of this, we would like to, what is conventional is to regularize them. So, hence, we use a regularization, and in particular, a specific one, which is called the dimensional two-dimensional regularization, in which instead of integrating things in 4 dimensions, you want to integrate them in 4 minus 2 epsilon dimensions. Okay? And then at the end of the computation, you want to set epsilon to 0 to recover physics in 4 dimensions. Okay. So what I'm going to do is, first of all, I would like to translate this kind of integration into the kind of twisted periods that we've seen before in the previous lectures. And in order to do that, let me use translate the integration over loop variables to Schwinger parameters. Schwinger parameterization. And I will not derive it fully, just motivate it, because I hope some of these things were seen before. So let's say I have some denominator, could be one of those, and let me allow it to be raised to some integer power. Okay, so I could have had some this propagator raised to power 1, mu1, mu2, mu3, and 4, and so on. And then I require that all of the mu a's are integers. Possibly 0, possibly 1. And then what Schwinger told us to do, well, is first take one of those expressions and write it in the following representation. Okay. About this coordinate z is that they parameterize the length or the proper length of each edge. Okay? And the z's are called Schwinger parameters. So then starting with a generic integral, which I will define, so let's say this guy is defined as I of this, as a parameterize with 4 exponents, mu1 up to mu4. In general, we'll have something with p propagators, which can have some p exponents, mu a. Okay, so these kind of integrals are given as, let's say we're at loops, capital loops, which have integral in d dimensions over each loop momentum. And then in the denominator, we have these p, capital P denominators, which was called dA. So these are some examples. Okay. And the state is that this kind of integrals can be always massaged after some prefactors to integrals of the following form, plus e, and then there will be e to some epsilon. W. Some forms. So this guy is potential as before, and then we spread it out over this. And this is a P4, holomorphic P4. And essentially what you do to get from here to here, you use this Schwinger trick P times, and integrate out the remaining Gaussian integrals over the whole. I will not do it explicitly because it would not be instructive to spend half an hour describing this. So let me, you can just trust it. Okay? But let me at least give you an example. An example would be for this box integral over there. So an example for both box integral. So all the momenta are massless here. And in this example, the potential W is equal to log of just the sum over all z's. And then two terms which are quadratic like this, E over S is equal to Z4. So for the experts, these polynomials here are related to semantic polynomials of the given graph. Let me notice one fact, is that the kinematic variable here enters kinematic variable. Enters only here. And I can always call it some, it only enters as T over S, so I can just call it some cross ratio, some ratio 1. Okay. So that's almost we're almost done. I need to specify what these V's are. These V's are simply given by some forms where I neglect the normalization of the type given to us by shrinking. Like so. In this case, I'm going to capital P for permutators. Okay, there's one caveat though, which I actually probably didn't spell out at the beginning, but there was always an assumption that the whole divisor of our forms, in this case, capital P, capital Pi, has to be contained in the whole divisor of our derivative of the potential. Okay, that was always a silent assumption, which was sort of trivially satisfied before, but now it's not. Because this form can have poles and in which each ZA equals to 0 or infinity. And that means, to fix this problem, I need to add some terms to the potential, and I will add it in the following way. There will be some coefficient delta, and some log of each ZA. Okay? In this way, D of W will contain a factor of dZA over ZA, and we will introduce the poles that are required here. And at the end of computation, we want to take the limit in which delta goes to 0.
It's just saying you want e to the W to regulate the integral.
That's another way of saying it. Okay, very good. So now we have these integrals, I of V, let's specialize this case in box, in which case, with some integration, the domain of integration is just R plus to the 4, and the form is specified by this form. Okay. So this can be understood. This is a pairing between two homology and cohomology. The fourth homology on this resulting space. So this would be C star to the 4 minus the e to the W equals to 0. Like so. In particular, the space on which everything is defined is the C star to the 4, which which is the space of the Schwinger parameters, you can call it the multi-space of metrics on a box graph, minus the places where this e to the w is 0. Okay, so that's a simple generalization what we had before. And as before, there is a corresponding homology, which is the same, defined of the same space. It's a model system defined by this potential function W. Okay, so now we can ask, well, how many integrals in dimensional regularization, how many integrals of the stack do we have? Okay, and that's answered by computing the rank or the dimension of these homology groups. So as before, things are concentrated in the middle dimension, or only the middle rank is non-zero. And that means that H4 EW, so it's the notation for this guy, is the only non-vanishing guy, and therefore it's equal to the -1 to the 4 of the Euler characteristic of the corresponding space. In order to avoid, actually, that we only place it here, so we can just copy it. Okay. So now the computation of this physical question became a mathematical question. Unfortunately, this is now more tricky to compute. So what you have to do is it's difficult to do it by hand. So what you do is you run some package in Moduli, and it computes with this Euler characteristic, and it turns out to be free. Alternatively, what you could have done is that we've also found in the previous lecture we found that we can solve the critical point conditions. So this, and count the number of critical points. Something that we can do algebraically, and then we find that the number of critical points is equal to -1 to the 4 of chi of this space. And chi of the space is equal to the number that we want to find. So what you can do is you can plug in this condition, this equation, to Mathematica, and find that indeed it has 3 solutions, and therefore there are 2 critical points. Okay, so now you're free to choose the basis that you want. And the choice that we made is the first form is going to be capital Phi of 0, 1, 0, 2. Next one will be 1, 0, 2, 0. And the final one is 1, 1, 1, 1. So the 1, 1, 1, 1 just means that we have our original box is in the basis. Every propagator to found 1. This guy means that we don't have 2 propagators, so they get pinched, like so. And one of them is with power 1, and the other one is with power 2, so it sort of counts as a double propagator. Then you do it as a heavy number. Similarly, if this this dude here is going to be this diagram, where one line is with a single denominator and the other one with a double. Okay. So these things span the basic, contribute the basis of this converge. Okay. So why is it important? One consequence is that any other integral such as this one, some arbitrary thing of this form, written in this bracket notation, can be expanded. It's always guaranteed to be that you can expand it in this basis. And the way that we will do it concretely is by playing our old trick, by inserting a resolution of identity here. And the resolution of identity will be in the space of twisted forms. Okay? So the simplest way to write it down is as follows: that r to the 4 plus some basis of this type, and then a dual basis with the original integral, with the original form. Okay, so what this told us is that the original integral with some arbitrary denominators can be expressed into a basis of these three integrals, and the coefficients of this expansion are just given by these intersection numbers. Okay, so now they have a different interpretation as computing the coefficients of this expansion. It turns out that these things can be done quite generally, and there's a body of work of Australia et al. Who exploited this kind of relations for more complicated integrals.
So here the fact that delta is non-zero is sort of very important, right?
I
mean, so delta is like the dim reg epsilon. Is that right? Is
Yeah,
delta
just
related?
that
You haven't said the word dim reg, but that is.
well, there's a separate. So these integrals are of the form integral e to the epsilon w. So epsilon is already here.
Oh, okay, right. Sorry.
This is a separate regulator.
Okay.
And it was used so that we can set up this problem in the language that we talked about before
Okay,
in
sure,
the first place.
sure.
Otherwise,
Okay.
we just couldn't do it.
But just super naively, with epsilon 0, I mean, compared to things that we normally say, we would say that there's a box, 4 triangles, and 2 bubbles for this problem, right? And maybe there were some relations between them, but that seems like more than 3.
It seems like one.
Yes. But you're saying that at finite epsilon, there's actually relations between them. Just like at finite alpha prime, we get relations between the different objects that we don't see at alpha prime equals. So the relations must involve one of our epsilons in them, of course. Then. Okay.
So all these statements are in Dirac. There will be a lot of accidents if you go in like 4 dimensions or 11 dimensions or whatever. There will be some accidental relations which are not seen in this formalism.
So how much does it then depend on your...
Yes.
Sorry. How much does it then depend on what you choose, like this function behind this delta to be? Could you regulate it differently? Like if you didn't choose a log, but like some
I think
1%.
nothing will change. Nothing should change. You could have. Well, log is nice because d of that is poles, logarithmic poles at both 0 and infinity. If you put say za to some power, we would only have poles at infinity, so we would have to do it separately. So log is nice in that sense, but probably not much changes.
So there are more relations in 3 dimensions than in 4 dimensions, right? That's what you...
Yeah.
I think that's a conclusion.
More relations.
No, so the accidental thing, so that thing you said about accidental is the other way around. Right?
Yeah.
It's In
No, I
equals four, you
said,
lose
but-
some.
There are more relations, fewer independent intervals, just like non-zero alpha prime versus alpha prime equals 0.
But I think it could be both, like, it could happen both ways.
Oh, I think maybe there's things that integrate to zero, to
Yeah,
order
the
epsilon
balance.
to the zero.
Yeah, exactly. Yeah,
That's what.
yeah. That's why it could either decrease or increase. Yeah.
But do you have any example of these relations between these integrals?
For example, can you write I mean, maybe you're gonna do it, but
Yeah.
there should be a formula, triangle equals, I don't know, box minus bubble.
Yeah.
There
Minus
is-
the top bubble,
There is
right,
like-
yeah, right, yeah, I know, right, but,
Triangle
Yeah, but,
equals 1 over epsilon bubble.
right, triangle equals 1 over epsilon bubble, that one makes, well,
Sorry, no.
oh, this is a massless
It's the
triangle.
other way. Epsilon times triangle equals bubble.
Right, right. Okay.
Very good. Any other questions? Okay, if not, then let me present an alternative point of view of what it means to compute Feynman intervals. And this is the one that is actually being used in practice in a lot of explicit computations. So alternative in the view is to consider kinematic space here, and consider your full space to be a fiber bundle or a kinematic space. Okay, so each point here will be labeled by this M. So let me call this M. So this is the kinematic space, this is the Moduli space, and here we define these homology groups and homology groups. But it's useful to think of defining integrals as being defined in both spaces. And then what we want to do is actually integrate out the Moduli space, and we are left with some form on a kinematic space, or a function of kinematic space. Okay? So concretely, what we would like to do, what people do in practice, is that you want to be able to walk from some singularities around this Moduli space, around this kinematic space, like so. So what that means to walk is to set up some system of differential equations that allow you to evolve the equations from some singular point where you might know how the integral looks like, and then evolve it to a point where you actually want it to compute. Okay? So for this, we need to set up differential equations. So let me introduce a differential on the kinematic space. And let me just call it dk. Okay? So for example, in the case of a box, dk, well, first of all, in the case of the box, k was a single, just consisting of a single variable, which was y, which was t over s. So in this case, this differential is dy then y. Okay, very simple. And then the question we would like to ask is how to do it more generally. Okay, so what we want to do is compute dk acting on the basis of some integrals, like so. Okay? So dk acting on the integral of the form, of the following form. Yeah, let me introduce, this is A, to label some basis, you could say 1 to the order characteristic of M. Okay, so what we do in the next step is just hit this derivative first here and then there. And what we find is if we want to pull out epsilon to the w, inside from in the form we will find dk of phi a. And from the other term, we'll find, since the single power of the epsilon is of e to the epsilon is pulled out already, just find plus epsilon d k w h by k. Okay? But the point is that this object here is still a form. So this is still a form on M. And what we can do, so let me just put it by a tilde. So what we can do is just project it back into a basis using this formula. Okay? So what this looks like is we'll end up with a sum over the basis. So it goes from, let's say, string down to the size of the basis. And then these terms will be some basis integrals that you chose yourself. Like the ones we had originally. And these fields are just intersection numbers. So here we need this is the summation index, so this is B. And here you have B dual and 5. So this guy is. Okay. Any questions? So in other words, what we found is that we can characterize the basis of amplitudes as follows. So we understand them as a section of this connection, where D is this object from here, and then omega are elements of this intersection matrix. Okay, this is just rephrasing of the original part. And then this I is just the basis of this interface. So I can include that. Okay. And that's precisely the structure that allows us to walk around the space, as long as we know the boundary conditions. This is a differential equation. Finite integrals with the same topology. Finite integrals. And alternatively, you can understand finite time integrals as a section of any vector bundle with this connection. Very good. So now, in order to actually characterize the spaces, instead of using an integral representation, you could have handed someone this matrix of capital omega with some boundary conditions, and it would be equivalent to specifying the original integral. Okay? And actually, and people use it in practice in many cases. So to complete the picture, what we need is a way of actually computing these omegas. We need to find omegas. Okay. And it so happens that some things are known about this omega. And one thing that is known is that if it contains any poles in epsilon, these poles would have to be spurious. Therefore, it must be a polynomial in epsilon of this form. at least we can take it as an assumption. On the other hand, we know that this omega is just a matrix of intersection numbers, which we discussed in a lot of detail in the last lecture. So there are two ways of actually computing these objects. Either you can start expanding around epsilon going to 0, or you can start expanding around epsilon going to infinity, and you will get the same answer in the end, because the series truncates in either way, because it was a polynomial to begin with. So the idea is very simple. Use this version. And the reason why we want to use this version is that we've seen some interesting things happening in epsilon going to infinity limit, in alpha prime going to infinity limit last time. So there's a hope that something similar will happen here. It's possibly slightly more general because we could have some corrections in leading order. But that's fine, because right now we understand to compute these corrections. So let me restate the result that we've seen on the blackboard at the end of the previous lecture, which is that it's some phi plus and phi minus in some top form, which in this case top form B. And it was divided by this is actually not the way that it was stated, but if it was stated, then it will be easier for generalizations. But this kind of residue is called the Grothendieck residue. And it's defined as residue around B W is equal to 0. So these things determine critical points of some form, say eta. This is simply defined as 2 pi I to the power of t times these counter integrals for each component. So then 1, W, then 1, then 2, and to the right. Okay. And these things naturally localize in this sort of tubular neighborhood of each critical point, and that's what allows you to compute the actual residues. So in the previous lecture, we found this result. It turns out that there are corrections which can be easily generated. And the first correction is in 1 over epsilon, and it takes the following form. There's a 1/2 sum over I going from 1 to t. In the numerator, we have this combination minus and the symmetry. Okay, and there's a sum over I, and what the sum means is that here the I derivative del I of W will be raised to the second power. Okay? And then you can start expanding higher orders, so on, and you find similar results. So, in the literature on mirror symmetry, these kind of objects are called pair residue pairings. high residue pairing. Okay, so this would be the leading residue pairing, this would be subleading, and so on. So this mainly stems from the work of Saito in the 80s. And later on, people made connections to physics, although not in this context. Okay, so just to finish, let me give you an example of what the spin evaluates do. So the box in the bottom. Remember that there was a thing y, which was defined as the only kinematic scale as t over s. And what we wanted to find is a differential equation, which was dy ly minus some matrix omega wedge this basis of three integrals. And the basis was of this form. So, using the first two pairings, you can easily compute this in terms of, or expand the corresponding intersection numbers using the starting. And if the answer that you find is that this matrix is equal to epsilon dy. That was, of course, a result we just known before. However, now it was reproduced, rather surprisingly, from the limits of intersection numbers, which were localizing on the critical points in the epsilon going to infinity limit. And that's exactly where you would expect to find large dimension physics. Completely unexpected. So just to complete the picture, what this means physically is that the kinematic space, which previously we drew abstractly, now is the space of y. You can complexify it. And it has some singularities. Y equals to 0, y equals to -1, and y equals to infinity. And those singularities correspond to kinematic singularities. This in the T channel, this in the U channel. Oh, sorry, this one is 0. This is the U channel. This is the T channel. 0 is where T vanishes, and infinity is where S vanishes. So what this connection allows you to do is walk around this kinematic space, which has coefficients in its kind of integers. Okay, so with that, let me finish.
Do these higher residue pairings satisfy analogs of the global residue theorem? These are other things that are you're just defined out.
I'm not exactly sure what you mean by this question, but one thing that happens.
Well, I mean, it just means if you sum, yeah, if
the
you sum.
derivation of the global residue theorem from the Griffith series.
Yeah.
It uses the check complex to derive it. And there, roughly speaking, you have some integrals over spheres. Later on, you translate into integrals over torus or over tori. And that's exactly what is used in this context as well. So the derivation is similar, although I'm not sure if that answered the question.
Oh, sorry. That thing is still an ordinary residue, just an ordinary residue for
residue.
like this
Yeah.
modified guy.
Yeah.
I see. I'm sorry. I didn't understand. I see.
Yeah, for this high residue pairing, do you still require the critical locus isolate?
Localize
In the
only.
previous talk, you require the critical locus for the W
Yeah.
isolate. For this high residue pairing, do you still require that?
Yeah, isolated and non-isolated. I'm not sure if that's a necessary condition, but that's just what was used here.
I don't think it's necessary. Anyway.
It might not be.
The kind of like boneheaded way of getting all of these, of getting both the basis and the differential equations and so on, is to just, in the end, they're all rational function identities amongst amongst the things that you're integrating, and so you can yeah. So anyway, you write things down. You write down total derivatives.
Well,
You get shift relations. I understand.
That's
This
how
is what
people
you're
do it
right.
even
That's
now.
right. That's
Yes.
right. That's how people did. Yeah. Sorry. Yes. That was not meant as an insult. But anyway. Yes. Right. So so there too in the end. So even forgetting about dim reg for a second, just purely at the level of standard integral reduction, right? Standard integral reduction is just statements about essentially partial fractions or simple identities about the integrand. They're purely algebraic operations to figure out what the coefficients are.
Yeah.
Here too, you end up getting a sort of purely algebraic operation to figure out what the coefficients are. So what exactly is the difference?
So the difference is the way that you actually compute the result. So what Nima was mentioning is that the standard way of performing this kind of reduction would be to consider zeros written as d of something. And that d of something typically turns out to be a combination of Feynman integrals.
What I was saying was even dumber than that, right?
Yes.
What I was saying was even dumber than that. What I was saying was just you don't ever see double propagators, you don't see anything like that. Just purely at the level of you have a bunch of denominators and then you expand the numerator in terms of anyway. I mean, just usual reduction for how you can go from very complicated things down to boxes, triangles, bubbles, and so on. So that doesn't even use a total derivative.
Okay, in this case, so in this case, the size of the basis would be larger than
Right.
what you might have expected.
So is it the finite epsilon that it seems like the finite epsilon is the real magic here, because somehow that's what lets you see relations between objects that we normally don't think are related to each other. And once you're at finite epsilon, then that's what's letting you sort of access the same thing around.
Are you saying this would give him the integrand reduction at epsilon, like if you had epsilon, if you set epsilon to 0?
I don't. Well, that's really my question is what is the relationship between this and just integrand reduction? So I think with the but maybe you'd say that with the box we would say there is no. Yeah. Maybe this is too. Maybe we should discuss this offline. I mean, if we just start with the box, super naively we would say that I can't reduce the box. Of course, we can turn boxes into triangles by triangles are boxes with some point at infinity using conformal and so on. But we go from boxes to triangles maybe. Certainly we wouldn't see bubbles in that way of doing it. So this is more, of course, but it's not just you're also seeing these. You're also seeing the total derivative relation. So it's certainly better than that.
So the ones who are just using partial fractions and so on, those would be cohomologies with constant coefficients as opposed to.
It wouldn't even be cohomology because I'm not even seeing these. Yeah, but
okay,
yeah,
but it
right.
can be answered as the question you can ask is what is the dimension of that, and that's the answer to your question. How many dependent integrals up to partial fractions there are.
But the thing that this integrand level reduction has is a separate sort of geometric interpretation in terms of residues in loop momentum space rather than residual questions in kinematic space, which is what you're doing here, right?
Yeah.
So that's really my question, is that there are canonical objects in loop momentum space which are residues of the forms that you're integrating, And operations on those, algebraic operations on those guys give one way of doing reduction to some kind of basis. Then you have this thing, which involves, well, first there's an epsilon, and secondly, it's residual manipulations of kinematics, right? Yeah, in the end, they're algebraic, in the end, everything is just algebraic identities. And there's a residue theorem that tells you relations between these objects. That's the sort of juice. Yeah, I don't understand directly what the connection is between these two ways of doing things.
So if you have integral which integrates to 0 in 4 dimensions, like 1 over parity of pentagon,
Yeah,
does it just disappear, or it will be epsilon times?
No, it's epsilon
something
times
else?
It does not,
Yeah.
yeah, it does not.
Yeah. So this whole thing does not sort of play super obviously nicely with finiteness and 4 dimensions.
No, it doesn't even know
Yeah,
about
right,
dimensions
I know, I
specifically.
understand, exactly, it doesn't. So in particular, it
So
doesn't
as
know
long as you're
that.
at epsilon, you might as well be at the generic
Right.
dimension.
But your title mentioned 4 dimensions, so do you have a couple words to say about that?
Yes, absolutely. Because this epsilon is exactly the same one as we can in here.
Yeah.
If you consider the integral around, say, 5 dimensions, this would not would have subleading terms. The power of this is that we can obtain this expression over there from these two previous terms.
Ah, but good, actually, so if we started with the hexagon, let's say,
Yeah.
you'd just have a bigger basis,
I get that.
right?
We would have to try it.
Certainly you would, because there is a bigger, I mean, and yet in 4 dimensions, you know that most of that is a lot of it is a fake.
Well, particularly it's expandable in this space.
No, but
No,
he
no,
would,
no, not exactly.
no, it should be. I would, actually, is
Well,
that,
enumerators.
sorry,
You need to, you need-
sorry, well, actually, maybe I'm wrong. Is it, maybe reduction doesn't work that way. So if you have
I think it
a,
does. In the generic space-time dimension, hexagon would have much more than this.
indeed, right. And so it's not actually expandable. A hexagon is not reducible to boxes. That in a dim reg regulated hexagon in 4 dimensions is not expandable in terms of a dim reg regulated
Not
box in
to
4
all
dimensions.
orders.
Oh, got it. Of course, that's it. Okay, so the whole thing is naturally living in infinitely many dimensions. Begins. Yeah.
No, but each integral you have to start in certain. So the hexagon, if you want the nice differential equation, you need to start in 16. Otherwise, you're not going to get the same nice
No,
differential equation.
I don't think so. I think he's saying that if you take he says that there's a set of objects that are hexagons and things that you get from with collapsing propagators for hexagons, and there is a big system associated with them. But that system, even for hexagons in 4 dimensions, just does not close. It does not reduce to boxes in 4 dimensions. You really need hexagons, just because beyond at subleading order in the epsilon expansion, it's not true that a hexagon is the sum of boxes at subleading order epsilon. It's just obviously true.
But even there, in that equation, you see
Yes.
that the differential equations for the bubbles have these dots, these twos somewhere.
They weren't necessary.
They weren't necessary, you could have chosen.
Yeah, but for the bubble, yes. But in general, I think what you discovered, that thing is just a 2D bubble. Like if you put a dot on a 4D bubble, that is just a 2D bubble. And I think the same thing is going to happen. Like you're going to find some nice basis, and then you're going to rediscover the 6D hexagon as one element of your basis that satisfies a nice differential equation. Of course, you can start in whatever dimension you want, but in the end, you're going to go back to.
This is what Montoya claims, right, is that you can construct these spaces that are finite in even numbers of dimensions.
But that means that, I mean, practical purposes is perfect, no problem. But conceptually, if you want to think about even one loop amplitudes with 100 particles, the way we like to think about them in 4 dimensions is really they're a sum of a bunch of boxes. Well, it's a simple things, and it reduces to something simple because we can't cut more than 4 lines.
Here, the
4
number,
dimensions.
the size of
Here
the
you
basis
have
is
to,
just
here's
zero.
the size of the basis. At finite epsilon, it's just arbitrarily big to begin with. So reduction does not commute with this picture. Like naive reduction does not commute with this picture.
I mean, so what Simone and I are doing is basically having the relative homology. So you can play this game directly with 4 dimensions.
I mean, what you want is to just use the epsilon to extract the divergences. I mean, naively, what you want is to just use except here the epsilon is doing 2 things. The epsilon first of all, it gets rid of divergences normally. Secondly, here it's doing something useful to allow you to relate objects that you didn't think were relatable to each other. So the question is whether you can have your cake and eat it too. Can you just use the can you both use the epsilon to only get rid of divergences and use it to like simplify basis and relate things? Somehow the way it's relating things is exactly by taking advantage of the divergence. Our epsilon times triangle equals a bubble type force, right? But the question is somehow whether one can have our cake and eat it too. I don't know.
Yeah, we have to add a curve direction. Yeah, but then the rest is 4 dimensional, and you do get the relations between them. But it matches nicely with this residue picture.
But there is no picture here. You don't have. Does anyone have a picture where the basis is close to boxes, triangles, and bubbles in 4 dimensions? Probably not. Or,
Not yet.
Well,
The way of
if you don't-
truncating it, say that.
Yeah.
Sorry, but the usual way of calculating cuts are still mod total derivatives, right? Like I cannot distinguish two integrals that differ by a 4D total derivative by calculating cuts, right? So if you think of the usual reduction as just doing
No,
cuts
but
in
the
4D.
usual reduction is kind of is a little bit orthogonal to this because we just never talk about total derivatives. But we think, oh, how stupid not to write down total derivative. Except it's not that stupid because we also don't see double propagators.
No,
right?
I think there's
so we
two
just
types.
live in the world of simple things with like ordinary non-double propagators. And in that world, reduction is a very powerful thing. I mean, it works and it gives you a unique answer at one loop, right? So now we're asking a different. But now you want to do something. Anyway, they're just separate things, right?
No, but everything I'm saying is that you cannot distinguish two integrands that differ by a 4D total derivative by taking cuts.
Definitely not. But we don't talk about those
Right,
when
right,
we do
right.
integral reduction because we disallow double propagators.
Right.
Okay, that's just what I'm saying. So if it's true, if you're going to allow general powers, you'd have to be a moron not to allow these, right? But people weren't morons, so they said we will stick with single propagators, right? And so we stick within the world of objects that actually make sense as Feynman diagrams. It's coming from ordinary Feynman diagrams. And in that world, there's an algebraic way of getting the answer, right? Just doing algebraic reduction. So we have two different things that yield a finite basis of objects, and they're different, and I'm trying to understand the relation between them. But one of them is sort of intrinsically infinite dimensional, and the other one is not. So they're not going to have a simple relationship with each other. But yes.
So what happens with slightly degenerate objects where in DIMREC we have this cancellation between IR and UV, so the result is 0, like bubble with one external leg and 3 on the other side. How would it fit here?
I would have to try it. Okay.
Just the massless bubble.
Yeah, massless
Just the
bubble.
massless bubble.
Normally we say that
The
it's
massless bubble
IR
is
and
0 and
UV and
DIMREC,
it cancels, but
Yeah, actually.
because you don't regulate divergence, yeah.
Well,
how
this
does it
is the
fit
sort
here?
of this is the technicality that we avoided in the previous discussions because for like in the string integrals, there's always for any ordering for any integral, as you were saying, there's always some choice we can make for the kinematic invariant to actually make the integral honestly convergent. But in DIMREG, we can't do that. For the massless bubble, we just can't do that. For the massless bubble, there's no choice of epsilon, which cancels both the UV and the IR divergence
Yeah.
at the same time.
So within the
Right.
setup, you can employ the regularization of the fact that we explored in
Uh-huh.
the second lecture, and there you would make sense to talk about this case.
Right.
It might not be physically,
But maybe you get a different, does it show up maybe with your, oh no, the sort of deltas go away in this answer in the end.
yeah.
I see.
This is
So-
finitely done.
But maybe if we did it that way, you'd explicitly have an epsilon UV and an epsilon IR. And then, so we'd see it explicitly as a 1 over epsilon UV minus epsilon IR type property. Yeah. But I actually don't know how to, I mean, the way DIMREG works is to just put these propagators to the minus epsilon and that just most dumbly. But there's no direct way of doing that to make the answer convergent for the massless bubble. So whatever you're doing has to be smarter than that. Any other questions for Sebastian? You're going to be here all week, right? You're okay, awesome. Well, let's thank him once more for a spectacular series.